Okay, question 5. There's the graph. We're on the same network, but we now need to apply Dijkstra's algorithm, to the network. Off we go. Starting at A. Okay. So we put things in very carefully here. We put a 1 here and 0 to illustrate that it's no distance from A to A. We then update the working values. 8, 0 plus 11 is 11, 0 plus 16 would be 16. We now choose the smallest working value to make permanent. So that 8 becomes permanent. The second one for us to do that. 8 add 14 is 22. 8 add 24 is 32. 8 add 20 is 28. And 8 add 10 is 18. But 18 is worse than 11, so we don't update that number in that box. The smallest working value now is 11. Make it permanent and work around the ones connected to that. 11 add 24 is 35, which isn't better than 22. 11 add 8 is 19. That improves on the 28, doesn't it? And 11 add 5 is 16, which is the same as that 16, so we don't need to write it. Our smallest working value is now the 16 here. Make it permanent. 16 add 7 is worse than 19. 16 add 18 is 34, which is worse than 32, so we're not going to update. And that was all that were connected to it. 19 is the next one. Make it permanent. 19 add 15 is 34. That doesn't improve on that, so we don't write anything. 19 add 12 is worse than 22. We don't improve on that one. Make that one permanent. 22 add 9 is 31, which is better. And so that's the last one to become permanent. There it is. And of course, when we mark this, we are looking for the working values all being correct. So those two are significant, because there we had to improve our working values. So the person marking it will do that. I've missed a working value out as well. Oh yeah, look, I'm sorry. I just noticed it. That's bad, isn't it? Yeah. What should we do? Should we do the whole thing again? Should we just pretend that we didn't do it wrong?
Do the whole thing? The video again.
How did I miss it? Schoolboy error. When we had this one as the third one, 11 plus 24. No, that's not the one. Oh, I missed it right at the start. 23. I didn't put that in there.
You can just write it in now.
I would have lost a mark. I'm going to write it and pretend that it's right. But you notice, I mean, you see how easy it is to lose credit for that. I would have lost a mark for this because I've not got all my working values in the right place. And right at the start of the question, I didn't update all of my temporary labels there. Right, we need to say what the path is, what the route was. We've ended at G. 31 take 9 is 22, so we came from F. 22 take away 14 is 8, so we came from B. And 8 take away 8 is 0, so we started at A. So that is the route. And I write it in that order. It's A to G that we're going, so that we get the credit the other way around. Then, now this was quite an interesting question. Dijkstra's algorithm, we're told, has quadratic order. That means order n squared. It takes 2.25 seconds for a certain computer to apply it to 7 vertices. Calculate approximately how many hours it would take to do 1,400 vertices. So remember, we've done one of these before, and the way that I like writing these out is we're told 7 takes 200, was it 2.25 or 225? 2.25 seconds. We're then saying we go to 1,400 items instead. So that is a 200 times increase in the size of the algorithm in the value of n. Now if n increases 200 times, the time must increase 200 squared times, because it's a quadratic order algorithm. If we times 2.25 by 200 squared, we get 90,000. But that was 90,000 seconds. And the question said, calculate approximately how many hours it takes. So here we have 90,000 seconds. We need to turn it into hours. 90,000 seconds. Well, if we divide by 60, that tells us that is 1,500 minutes. And if we divide that by 60, it's 25 hours. So that was what you needed to do. And quite a few people got 90,000, but didn't get to 25 hours at the end of it.
I got to 25 hours.
We've got 50 hours on mine.
Oh yeah, so how many hours? So, yeah.
Wouldn't be more helpful.
I'll have a look in a moment, David.
The rotation around the y-axis is x squared.
Marks. Right, part 3. How much shorter would... This is a bit weird, isn't it? Because this doesn't almost feel like it's on the same question. You just said something bad, didn't you? Right. How much shorter would CE need to be for it to become part of the shortest path? Well, if that were going to happen, quite a few people got this wrong as well, but if that were going to happen, let's think logically. If CE was going to be part of the shortest path, then 11 plus 15 plus CE would have to be less than or equal to the 31 that is our shortest path. So we're just going to set up a little linear inequality. We're going to say that 11 plus CE plus 15 is less than or equal to 31. In other words, x is less than or equal to 5. It's currently 8, so it needs to be at least 3 shorter. In order to be on the shortest path. Quite a few people put 4 there, because of course if it was 4, it would definitely be on the shortest path, but we could have 2 shortest paths, and so if it was 5, it would be still on the shortest path, just not a unique shortest path. Does that make sense? Right, finally, it says, following a landslip, the paths AC and CE become blocked and cannot be used. A warden needs to travel along all the remaining paths to check that there are no more landslips. Find the shortest distance that the warden must travel. So, remembering what's happened with this question. Now, look, we've blocked AC and CE. So they're no longer there, and we have to travel along all of them. This has turned it into a Chinese postman problem, isn't it? Where you have to travel along every road at least once. So that's all about what are the odd vertices. I'm going to do my working out up here for this now. The odd vertices. Now, well, A would be odd now because we've lost AC. So A is odd. C would be odd, 1, 2, 3, because we've lost 2 from there. B, 1, 2, 3, 4, 5. B is odd. And 1, 2, 3, 4, 5. F is odd as well. So they're the odd ones. Now this is where this was a little bit sneaky, because we do that thing of pairing them up. So we're going to pair AC with BF. And you may fall into the trap of saying the shortest path from A to C is 11. So the whole point is that AC is blocked. We can't travel along it. So to get from A to C, actually, you have to go via B now in its shortest path. So that is 18. And BF, well that one's 14, giving us the shortest path there of 32. If we look at the next pairing, AB and CF, A to B is 8, C to F is 24. I know we used to be able to go along CE and then to F, which was less, that was only 20. But we can't do that anymore. So 24, is that the best one? It is, I think. Which is also 32. We could also go C to D to E to F, but that's 24 as well, isn't it? 5, 7 and 12 gives us 24. Right, the last pairing, AF and BC. A to F, the shortest path is, well, it's not that 23, it's 18, it's 8 plus 14, so it's 22. And BC, shortest path is 10. So look what's happened. We got 32 out of all of them. So we choose the smallest pairing. And we need to add that on. Now, remember what's happened here as well. The question did say the total weights is 224. But we've removed 2 weights. We've removed 11 and 8. So our total is 224. Take away the 11 and 8 that we've removed, and add in the 32 that we're going to have to repeat, whichever ones we choose to repeat, and that gives us an answer of 237. It was a bit sneaky, wasn't it? And the sneaky bit was that having once taken out these A, C and CE, you had to remember that you then couldn't use them to find your best pairings when you pair things up. That's the end of that question.